Okay, so the recording and the transcription have started, and as I say, I will make them available. Some of you may already have seen that we have a YouTube channel where previous lectures are placed, and I'll place these ones in the same place. So, what is the operating systems module? Well, what I want to do is add on to what you did with Henry last year when you did computer systems, and take that and build on it to help you understand how a modern operating system is created, the kinds of choices that we have to make when we're doing that, the effects of those choices, and why different operating systems might make different choices. Sometimes it can be really easy to understand. If you're sitting there with, say, a Windows desktop, you might have a hard disk in there. Not a difficult decision to make to allow Windows, the operating system, to support hard disks. Less likely that you're going to have a hard disk in your Android phone. So the Android operating system, not so happy about supporting hard disks because there's no point in doing it. So it's made a choice. And a lot of the stuff that we'll be talking about today is about choices. It's about the kinds of things that we have to do, the trade-offs as well. We all want operating systems and programs and computers that go as quickly as possible, but we also want them to do as much as possible and do as many things as possible. And you can't have all those things at once. You have to make trade-offs, and we'll talk about that as well. So when you come out of this, hopefully you'll understand about those structures, those functions, how they all work together, and to understand all the components that go into making an operating system. Now, unusually, certainly for me, and I think for all of your modules, I am asking you to buy a book. The book is called Operating Systems Concepts. And I've put a link to it on the screen there, and I'm just going to bring it up. This is Amazon. Other vendors are available. So you'll see that Operating Systems Concepts is quite expensive. So don't buy that one. Okay? Don't buy that one. I don't want you to spend £86 on a book. I don't even want you to spend £35.78 on a book. What I want you to do is go in to Amazon or somewhere else and find previous editions. You'll see that they all have dinosaurs on the front. So go through, find, as I say, a previous version, excuse me, and I don't mind which, and buy a second-hand copy. Now, the thing about the book is operating systems are similar. So things change, of course they change, but the underlying principles stay the same, and it's part of the reason I want you to buy this book. And here, the first one I've clicked on, and you can spend more time on it. Here it's down to a £5 for a used version. I bought mine for a penny plus £2.80 postage, so look around and get a cheap one. If you really can't afford the price of a pint, there's copies in the library, but I really do recommend you buy it because it will be helpful not just for this module, but for other modules and in your career. Because as I say, operating systems don't really change that much. The underlying concepts haven't changed that much. And all the material that we are going to cover will be in all the editions of this book. The newer editions actually give examples of different operating systems. So older versions might say, here's a Solaris Unix operating system and how it works. And a newer version might say, here's a Windows 7 operating system and how it works. You don't need those chapters, but the basic stuff is similar in all of the editions, so buy a cheap version. But please do buy the cheap version because all of the stuff that we are doing is based on this book, okay? So even the lectures, the slides, they're all coming from this book. So it will be really helpful for you to have. So spring a fiver, or if you can do it, spring a penny plus 280 postage and buy the book, please. Because the books are the same, but might be slightly differently ordered, what I've done is created a document that lets you see where we're working. Now, you've had an email and all of the module materials are in that link from that email. So it's in something called a OneNote document. So OneNote's like Word on steroids. It's not just text. It can have images and spreadsheets and presentations and YouTube videos. There's a YouTube channel, for example, for this module. So all of the information that you need for this module is in this OneNote notebook, and you'll see that it's organized by chapter. So there's the chapters in my edition of the book and the material that we're going to cover. So there's processes, and you can see we've got a presentation, we've got tutorials about them. Different things to do, different tasks. Okay, it's all in this document. So you've got access to everything that we're going to use from day one. So you can, not only can you work ahead, you should work ahead. So today is the introduction. Next week, we start on system structures. So you should read that stuff before we get there. Thanks, Connors. Connors found a cheaper one. So yeah, read the stuff before you get to the next lecture. So you should be reading system structures before next week. What it means is rather than coming in here and me just talking at you, it means we can cover what's in there, but you've already read it, you've already thought about it. It means you can ask me questions about it while we're in here. Now, to help you better understand the different editions and to understand what we're doing, one of the documents that we've got in this OneNote notebook is the syllabus. Basically, what we are doing and when. So this is week 2. UWS starts weeks at number 1 with the induction week. So the first teaching week is number 2. And you can see that's the week beginning the 12th of the 9th. So for you guys in Lanarkshire, that's actually the date of your lab as well. You guys in Paisley, it's not. So I've just put the week beginning to cope with the different campuses. And you'll see what we're doing week by week. So this is semester week 2, it's our first week. We are doing the introduction chapter. Next week, we're doing the system structures chapter. Next week, the week after that, we're doing process concepts and so on. Now, one of the reasons I've put that there with the chapter names is that different editions sometimes swap the chapters about. The content's pretty much the same, but they swap the order. So chapter 3 might become chapter 6. But as long as you've got the names, you should be able to find it in your book and be able to get the information there. Final thing about the book. Now, I've said it will be useful for this module, for other modules, and throughout your career, and that's true. And part of the reason for that is it's a very comprehensive book. And I meant to bring my copy and I haven't, but it's, you know, it's this thick. It's a big book. And we're not going to cover all of that book in this second year module. So one of the other things I've put on there is the sections that we're not doing. So you can see there that in chapter 2, we're doing up to 2.5, but 2.6, 2.8, 2.9 we're not doing, okay? So we're cutting out a lot of it. Ryan's asked, does it matter what edition or year? Nope, it doesn't. And that's exactly what I'm saying now. It doesn't matter what edition, what year, the core material is the same. Just get the cheapest copy that you can find. You won't be disadvantaged. Okay, so you've got what we're doing every week. You've got the chapter, and you've got what we're missing. Sometimes, actually, we miss out whole chapters. So we're not doing the chapter on synchronization or the chapter on deadlocks. They're just not happening. Okay, so you've got all the materials, you know exactly what we're doing, you know the order that we're doing it in, and you've also got when the assessments will be due, and I'll talk a wee bit more about the assessments after. So if you haven't yet accessed this OneNote notebook, please do. I sent you all out an email with a link to it. In that email was also an invitation to join our team. Not everyone has done that yet. If you haven't done it, please do. And part of the reason for that is if you join our team, I've actually put those things into the team as well. So there's a link direct to that OneNote notebook in our team. Now you can see exactly the same document, albeit loading very slowly because I've got a very old machine. So all the stuff that you need is on Teams. So if you haven't yet joined our team, please do. The link again was in the email. All happy with that? I'm not seeing any more questions in the chat. I'm not seeing any hands. Okay. So, oh, David's bought it already. Always ahead of the curve is David. So, all the materials aren't available on Moodle, despite what it says there. So, you'll know that the university is changing its VLE. So we used to use Moodle, which is what it mentions there. Now we use Aula. Part of the problem is that Aula doesn't support some of the assessment types that I do. So rather than having Aula and Moodle and Teams, that's why all the module materials are on that OneNote notebook, because it just means I can link to it from wherever. And I can't even remember, I think I put a link to it on Aula. So we are still using Moodle, but we're not using it for the module materials, but we are using it for the assessments. So if you go to Moodle now, you'll see that all we have is tutorials, tests, and assessments. Okay. I've taken out all the module materials and they're on that OneNote notebook. And if you're wondering what I was talking about in terms of the email that I sent you, I basically copied it into Moodle as well. And if you haven't got the Teams invitation, there it's there. So you can follow those instructions there. So I've put them on there too. And again, if you're not sure where Moodle is, it's at my.uws.ac.uk. But of course, you'll know that because I put that into the email as well. There it's there. But also, just like with the module materials, I've linked to it in Teams. I won't bother logging in. So you've got links everywhere. David's asking for a copy of the OneNote so that you can have a local copy. And Connor's given them the link. And what Connor's given them is a link to the notebook. That's correct. And I'm not sure at the moment whether you can copy from that or whether I haven't given you the rights to. And the answer, David, is yes. If you want something, I'm happy to supply it. What I'm trying to remember is there was an issue with permissions in that they're not very fine-grained, in that I could either let you look at the notebook or I could let you edit it, and there's nothing in between, so I couldn't let you copy bits out of it. I think that was the issue. But I'm more than happy to give you copies of it. And in fact, what I'll do is there's something on Teams called a class notebook, and I should be able to copy them into that class notebook, and then you get your own copy. So I'll make a wee note and I'll do that. Connor sent a link which isn't the module materials, it's a student information. So there's general information as well. Again, you had a link to this, and it's all the sorts of stuff that's general, and it's not even, I send this to all my students for all modules at all levels. So it's all the stuff about academic information and plagiarism and pass marks and accessibility and calendars and teams and referencing and just kind of general information that's helpful to have as a student. As I say, I send it to all of my students. I give them access to all of this. And particularly when you're going to be doing an assessment that requires referencing, it just means that all the stuff's there. And again, it's all there from day one. That said, I might add things to it. So a lot of these pages have come from people asking me questions, and I've created a page to answer the question so that it's there for future reference. And if you ask me a question, I might point to this and say it's in the student information, so go read it. So if you ask me about Aula, or how to access the library, or how to get onto Moodle, all of the things are in there. So please have a look at them first before you ask the question. I'm being asked for the code for Teams. So if you don't have the code, that's it there, and I'll just put it in the chat. So you should be able to join the team just by joining the team and putting in that code. So go to Teams, make sure you've logged in using your UWS credentials, join the team, and then enter the code and you'll be there. And Greer's asking for that because of enrolment issues, and that's, again, part of the reason I do it this way. It means that everybody can get access to things, even if we still have some slight enrolment issues. And it just means I can give you all this stuff without having to rely on it being accessed. So, for example, the module materials don't require any sort of credentials at all. And actually, just when I'm thinking there for David, that's part of the reason I don't let you copy it or edit it, because anybody who has that link can look at it, which is fine. I don't mind anybody looking at it, but I don't want just anybody editing it. But it means that if you're not enrolled, it means you can get access to the materials and you're not falling behind. Okay, so all the materials are available not on Moodle, but on the OneNote document, and there's a link to that on our team and in the email. And it's all relevant, except where it's explicitly mentioned that it's not. So it's all there for a reason. Having said that, I've explicitly said synchronization isn't in this course, but I have left in the slides for synchronization. So we won't be doing them in this class, I won't be covering them, but you might be interested in it. You might want to have a copy of that presentation, have a look at that presentation. That's fine. But we won't be doing it, and I've noted that we're not doing it. Similarly, where we have the presentations for ones that we are doing, you will see 2 lectures. So in the same way as I've noted that there's bits that we're not doing, I've cut stuff out of the slides for the bits that we're not doing. So there's a version for us, but if you want to see the original version, I've put that in there too, just for your interest. Okay, so there's a bit that we're doing, and then the bit that's the original. And you'll see that on all of these chapters, our version and the original book version. And invariably, our version is much smaller. All okay so far? Okay. So all the sections are there for you to do, and I would like you to turn up. There's stuff going on in the chat. There's people asking questions. There's things that I'm saying that aren't up on these slides. You don't get to see it just by reading the slides. If all you had to do was read, then I would tell you to go and buy the book, and I'll see you in December for your assessment. But of course, that's not what we're doing. So please turn up to these things. Turn up for these online lectures and turn up for your in-person labs. And we will take attendance. We are required by the university to take attendance. And if you don't turn up, well, you know the script. Okay, so how are we going to assess this? There are a few things. The first one is an individual coursework. So I've said that it's building on what we do in computer systems in first year, and I want to give you an idea of what's happening when we have to do anything on a computer, because it's very easy to get sucked into what's a computer. Oh, it's a thing that has a Windows interface and you click a button and something magically happens. But of course, that's not the case, as you know from last year. So one of the things that I want you to do is create a program using those very low-level instructions. We are going to use something called assembler. And you're going to create a program in assembler, just to give you a flavor of what it's like. Because what we think of as a very tiny thing to do can actually take lots of assembler instructions. And it just reminds us that the operating system is doing an awful lot of things. Man, I've got OneNote running, I've got presentations running, and I've got Teams running, and it's showing me live video. Think of all the things that are happening under the hood for that to happen. Think of all the things that the operating system has to juggle to make that happen. We sometimes forget, so our first assessment is to make sure that we don't forget. So our first assessment, and again, all the assessments are available from the beginning. All the explanations are on this OneNote document. It's something called the Little Man computer. So this is worth 20 marks. I've basically set it up so that it's 100 marks. So basically every mark you get is 1%, just to make it easy for us. So this is worth 20 marks or 20%, whatever way you want to think about it. Now, it's not exactly the hardest programming task in the world. Read 3 values and sort them from largest to smallest. So not exactly the toughest task ever. But you have to do it using machine code. Sorry, not machine code, you have to do it using assembler. Specifically, you have to do it using this computer. So what we've got here, I made a mistake there. So what I do is I have Firefox running, and that's the browser that I use whenever I'm giving one of these lectures. And I do that because I've made the mistake before of just using my normal browser, which is Chrome. And while switching from page to page, people were reading my personal email and stuff. So I thought I'll not do that, and I'll keep the work stuff in a separate browser. So I use Firefox, even though I use Chrome normally. But because I just clicked on that, it opened up in Chrome, and my machine just went. Ugh. So this is the little man computer, and you can see that you can write assembler code. So this is assembler here, LDA, STA, LDA, STA, INP, BRZ. Those are all assembler codes. You've done programming, so it's kind of like the lower level of programming. This is the RAM. So this is a RAM in your computer with machine code. Now it's in there as base 10, but this is actually binary. And what this thing does, and I'll choose a slightly less complicated one. So here's a program that adds two numbers. INP. Anybody want to take a stab at what INP might stand for?
Input.
Input. STA99. Anybody want to take a stab at STA? It might help if I say it's ST space A. What might ST might be?
Store.
Store. So it's saying store, and this mysterious A refers to the accumulator that you'll remember from last year. Store whatever's in the accumulator in memory location 99. We've got another INP for input. And then we've got, oh, this is going to be tricky. Can you work out what the command ADD might do? So we're going to addition. So we're going to add whatever's in the accumulator to whatever's in memory location 99. OUT. Output. So we have taken two inputs, we've added them together, we've said output, and HLT. Alt. Correct. So what the little man computer does is shows you what's happening. It's gone away. It knows that it's getting the instruction in location 0. So it's gone away and got it. It's bringing that back to the CPU. And once it's got there, it's putting it into the instruction 9, address register 1. And we've got a wee thing here saying inputs required, which isn't a surprise because our first command was input. So it's taking my input and it's putting it into the accumulator. And it's then looking at the program counter and it's saying next one is instruction 1. It also increments the program counter. It goes away to RAM. It gets whatever's in location 1 because that's the next instruction, brings it back to the CPU and splits it up between an instruction and a register. So the instruction is 3, which is store, whatever's in the accumulator, and the address says 99. So it goes and grabs that 8 and that 99 and it sends them down the address and data buses to store 8 in memory location 99. And it then goes to get memory location 2, so it sends 2 down the address line to get whatever's in memory location 2, and it sends that back up the data bus. And it's the same, not surprisingly, as was in memory location 0, because we've got two inputs. They're both the same, and it's looking for another input. But give it another input. That comes in, it overwrites what's in the accumulator, and that stays there just now, and it goes away to get the next instruction, which it knows is in memory location 3, not forgetting to update the program counter, so it knows the next one's 4. Goes away, gets the instruction, brings it back to the CPU, splits it up between the instruction and the address, and it says add. So it's add whatever's in memory location 99, so it has to go away to memory location 99, find what's in memory location 99, send that back down the data bus, bring that in, add it to whatever's in the accumulator using the arithmetic and logic unit, and that gives us 12 in the accumulator. And then goes and gets the next instruction. Instruction 4, it's also updated the program counter, goes and gets instruction 4, brings it back in. You'll be pleased to know that you can speed this up down here. So I'm going to speed this up a wee bit, brings it back, gets instruction 902. 902 means output. So it's output 12, which is our addition. And then it goes and gets the next instruction, which is instruction 0, which is halt, and it stops. Now, you lot were getting really bored with my voiceover there. You were getting really bored with me telling you what was happening. It was a way to get instructions, which bus it was sending them down, what it was doing with the input and the output and the accumulator and the arithmetic and logic unit. And that's just for adding two numbers. Think how much code is happening in your computer for it to progress the video that you're watching and the sound that you're hearing, and the fact that you've got other programs running in the background. So you've got WhatsApp chatting to your mates saying, is Tony ever going to stop talking? You've got all this stuff happening all at once, really, really quickly, and it's important we don't forget it. So that's what your first assessment is. It's to write a small program using the little man computer. So the online stuff, the first half of the module, the first 6 weeks or so, is to do the LMC. So I'll not be doing any more lectures on the LMC. You have got lots and lots of materials, lots and lots of tutorials, and I want you to run through these at your own speed. So there's written ones and there's also video ones. As I say, you can watch these actually in OneNote. You don't even have to go anywhere else. So all the stuff's in there, and this is self-paced. So I want you to do this on your own, but we'll be in the lab to help if you need it. When you've done it, you will submit two things. The design of your program, and I don't mind how you do it, if it's a flowchart, if it's pseudocode, if it's whatever, and also the code itself. In other words, this stuff here. And what I'm going to do is I'm going to take that code, I'm going to input it into this implementation, and I'm going to see if it runs. Okay. That's why it's important you only use this version, because there are tons of versions of the LMC out there. Only use this version, because this is the version it will be tested on. If it doesn't run on this one, I don't care if you tell me that it runs on the LMC that you built into Excel, and that's a thing, there is an Excel LMC. It doesn't matter. Run it on this one. The second thing is we'll be doing this in the lab, so we'll be looking at them in person. So I'll be coming around and asking you about them. In other words, I'll be checking if you know what your code does. So I might say, why have you put this instruction here? What's it doing? And it's just me trying to figure out whether you actually know what you're doing or whether you found a copy somewhere online. Okay. So if you can't explain your code, then you have a problem. Henry will be doing the same thing at Lanarkshire. And it will then be marked using the marking scheme that's there. So you'll see that there's a few headings: LMC, command set, program logic, commented code, redundant code, and so on. And you'll get marks depending whether you don't have any, whether you've used some, incomplete, complete, and so on. Okay, so there's a range of headings and you'll get marks based on them. You can also get extra credit. So if you want to extend your program for extra credit, you can. Don't forget to tell me what it is. So you might come in and say, oh, I have created one that copes with negative numbers, or it can cope with as many inputs as you want to give it, or, you know, you tell me. So if you want to get extra credit, write a better program and tell us about it. So that is the first assessment. Any questions on that? Okay. The second assessment is everybody's favourite because it's a group coursework. Change this. Whoa. Oh, geez. Well, see, the thing is, what I have under my desk is an add-on. It plugs into a USB connection, and it's wee pedals that lets me go backwards and forwards in the presentations without using my mouse. So if I'm marking up something with a pen, I don't use the mouse, I can use a pedal, and I just managed to rest my foot on the pedal, so it ran all the way through there. Sorry about that. So, second one, as I say, is everyone's favourite group assessment, and it's a report. There's a change from the slide. So instead of 3, I am happy to accept 4. So 4 per group. And in exceptional circumstances, by which I mean where the class numbers don't divide evenly by 4, I'll take groups of 3 or I'll take groups of 5, and I'll leave it up to you guys to choose. Now, I've got a whole big spiel on OneNote about me choosing random groups. And it's true. The reason it's there is because random groups work better for a whole lot of reasons. But I'm acutely aware that you guys are working in slightly different circumstances. So normally what would happen is you're taking this second year module, you kind of know people in the class because you had first year with them. And what I'm doing is trying to mix that up a wee bit when we get to this point. But I'm aware that you are working online. I'm aware that you don't know people as well. I'm aware that there are issues. So I'm actually going to give you guys the choice. So I'm going to put on Moodle at what I call a self-select. It basically sets up a whole bunch of groups and you guys can get together. So if you want to select a group on your own, you go into Moodle and say, yeah, we're in this one together. And if there's people left over at the end, I will randomly split them. So it's entirely up to you guys. You can have random or you can self-select. I don't mind. So I'll put that on Moodle and give you the chance to select over the coming week. There's a question on the chat asking about how many are in the group. I think I've just answered it. It's 4 now, but in exceptional circumstances, depending on the outcome of the division, 3 or 5, but 4 by preference. So what is this group report? Well, we're going through and we're talking about processes and threads and CPUs and memory management and all that kind of stuff. And I said right at the start that there's going to be choices that we make about these things. So what I'm asking you to do is choose an operating system and explain the choices that have been made and why. So, why has a particular operating system chosen a particular file system? And if you don't know what I mean by file system, don't worry, we're doing that in chapter 10. Why has it chosen a particular way of implementing threads? And again, if you don't know about that, that's fine. That's what chapter 4 is for. So what I want you to do is link the theories of the operating system and the choices that we make that we're going to cover in here to a specific operating system. And this year, it's going to be a Linux operating system. And I actually don't mind which one. You can choose whichever one you like. So if you have a preferred Linux operating system, great. If you've never heard of Linux, well, this is a good chance to get used to it. And if you've thought, oh, Linux, I have heard of that, I wonder what it's about, even better, because it gives you the opportunity to do it. There is information, not a good, not a good thing when I can't remember where I put things. There is information in chapter 2 about installing Linux. So you can do it virtually. You don't have to get a new machine. You can install it on a virtual machine. And there's links to lots of distributions and links to how to install things. And the example I've given is Ubuntu as an example. It's a popular Linux distribution, but if you don't want to use Ubuntu, don't. Okay. The other thing I would suggest is this is due in according to this syllabus. At the end of November. I suggest you don't wait until the start of November to start writing this report. Part of the reason I give you it out nice and early is so that you can write your report as you go along. So as we learn about processes, start writing your report on the processes section. As we learn about threads, start writing your report on the thread section and so on. And you can see with the marking system, the marking scheme, where you're going to get your marks from. And they pretty much correspond to the chapters. So there's marks for the overall design. And that's really this system structures chapter. There's marks for processes, which is in the processes chapter, as is scheduling. That's also in the processes chapter. There's marks for threads. There's marks for memory management, virtual memory, and then it stops. Why do you think it stops there rather than going all the way down here? Basically, I want you to give you time to finish your report. So the stuff that is required in the report stops about here, and that gives you 3 weeks after it to finish your report. So I'm not going to teach you about something in week 11 and ask you to hand in your report in week 12. So the stuff that's in your report, we stop a wee bit earlier to give you time to do it. Now, it has to be a professional report. You're starting to get further into your academic career, excuse me, so it has to be referenced. So it has to be properly constructed, headers, diagrams, attributions, all that kind of stuff. And again, if you don't know how to do it, that's why you've got your student information OneNote that tells you about referencing, why you have to do it, how to do it. And it's also got some tools to help you do that. Now, it's not a huge amount. So there's 5 marks for how you lay out the report, how you reference. So it's not a deal breaker in terms of passing the module. Because it's to get you started and thinking about this, because it will become more part of what you're doing as you go along. The question I always get asked is, how long does a report need to be? And the answer I always give you is, I don't know. You tell me. You know what the marking scheme is. You know what I want you to cover. You know what it is I'm asking you to do. Now, if the question was slightly different, if you were in a job and your boss said, I've heard about Linux, would it be feasible for us to switch away and use a Linux system in our company? Write me a report and have it in 2 weeks. Your first question to your boss would not be, fine, how many words do you want? It would be, okay, let me cover all the information. And that's what I want you to do here. I don't want you to think in terms of word count. Apart from anything else, you could put in a diagram and you all know the phrase. So I'm not going to say how long the report should be. I'm going to leave that up to your professional judgment. Cover what needs to be covered and make sure that it's all there. Any questions on that one?
Nope.
All happy? Okay, the final one is class tests. So these are traditional tests. They're knowledge-based. And this is part of what I was talking about earlier. So these are going to be on Moodle, so they're done online and they're marked automatically. We'll also use the on-campus lab time to do it. So there'll be a particular date that you're given, and we'll say this is when we are going to do it. So you will require to be there. Questions can come from all of the stuff that's on the module materials, excuse me. Now, part of the reason that I do it online is I've got hundreds of questions. So you'll get a question that might be on one of the sections. It might be on processes. And you might get 3 questions about processes. But those 3 questions will come from the 40 questions that I have in there. So you'll get 3 random questions out of those 40. So you won't know what's coming. It also means that you can't just sit in the lab and look at your neighbour and see what they're putting, because they'll have different questions too, more than likely. There's a question about maximum length for the group report. Again, there's no maximum length, but again, think about it in terms of a job. You want to cover the material, but you don't want to just drone on. So again, I'll leave it up to you. So the class tests will be randomized, and there are 2 of them, and there's a reason for that. There's 2 class tests because what I've done is split them up. So rather than doing all the chapters and then giving you one big 40-mark test, the first class test is for chapters 1 to 5, and the second class test is for chapters 8 to 13. So I've just split it up a wee bit. Rather than trying to remember what happened 3 months ago, I'm trying to do it as it's fresh in your mind. As I said, they are online, and that's part of the reason we use Moodle. And one of the nice things about using Moodle is that as well as actually having the class tests, you can practice for them. So for every chapter, there is a chapter test. Now, before I do this, I'm not even reading the questions. I'm just putting an answer and moving to next just to show you what we're doing. So this is the class test. You'll see there are 20 questions here for chapter 1. So that was a choose one from 5. This is a true or false. This is a multiple choice one again. This is choose more than one. How many of these are true? Here's a drag and drop. Take the words that are there and put them into the sentence to make the sentence make sense type question. Okay, so there's a few different types of question in there, but they're all online and they're all automatically mapped. And part of the reason I point this out is if you can do the chapter tests, you will be fine with the class test. So every week when we go through a chapter, do these chapter tests. And if you can do them, you will be fine. In order to emulate the class test itself, you'll see different ones. So here's a chapter test, but here's an assessment chapter test. Same kind of idea, but it's timed. Just like it will be in class. So you've got a time. What it's done is selected 5 random questions, given you time and said, right, go away and do these things. Within the same sort of time frame you would have in the class test. So if you have a spare 5 minutes sometime and you want to practice, go do the class test. And when you do, it will mark it and it'll tell you what you did. So I've got one here that was orange because I got bits of it right. I've got one here that was right because entirely by chance I clicked the right button. And I've got 3 here that are wrong because again, I just clicked whatever button came first. So you can practice for these class tests. They are sorted by class test 1. So that's chapters 1 through 5. And class test 2, chapters 8 through 13. Okay, so practice every week. And if there's bits in there that you don't understand, even though you've got the feedback, then ask us. That's why we're in the lab. For those of you doing cybersecurity, we also have the ones for the cybersecurity chapters. Any questions on that? No. Connor thinks it's cool. Thank you, Connor. I think it's cool too. Okay, so 20% for the LMC, 40% for the group report, and 2 tests at 20 marks each is another 40, and that gives you your 100. Usual thing, pass mark is 40. But each of those sections, so that's the individual bit, the group bit, and the class tests, you need 30% in each of those to pass. And part of the reason I do that is, again, I'm well aware that in some groups there are freeloaders who will just try and pass using other people's work. And by having the individual bit also count as to whether you pass it, stops that happening, hopefully. But you don't want to be at 40%. You want to pass everything. And you want to get as best a mark as you can, because it will affect your GPA. So, turn up, read the stuff. If you don't understand, ask, and we're there if you have any questions. And actually, I'm here right now if you have any questions. So are there any questions?
Yeah, I was just wondering, but is this online lecture 11 o'clock every week, or is it back to 9 next week?
No, it's 11 o'clock. So what you've got on your timetable, so the 9 o'clock is a hangover from last year. So we had the online lab at 9 o'clock. Then we had the online lecture at 11. Clearly, I'm not sitting in my office because it'd be hard for me to give this online lecture with students knocking on the door and with other people in the office chatting and on the phone. And the fact that I don't have a camera at work doesn't help either. So I do this here, and then I have to travel to Paisley to do the campus thing. So we'll finish this here and I'll jump on a train and I'll be on campus at 2 o'clock. The 9 o'clock one is where we can have a discussion about how we want to do it. So I'm aware that some people, and Lisa's just put a question in the chat about it. So it might be that some weeks we decide that we're going to do it online. So we might do week about. Now, this is for Paisley, to be very clear. So for Lanarkshire, speak to Henry. It's up to him how he wants to run it there. But for Paisley, you've got a timetabled on campus and you get a timetabled online. We will only do one or the other. We won't do both. So the 9 o'clock or the 2 o'clock, we will do the 9 or the 2. We won't do both. But we always do the 11 o'clock. You will have to come in for tests, not surprisingly. And I do want you to start coming in. And apart from anything else, we've been told to get you to start coming in. But I am happy to negotiate. And as I say, we might do week about. I'm not sure. But if we have an on-campus class, you have to be there. So for the Paisley students, I'll chat with you later and we can decide what we want to do.
Thank you.
Is that okay? Is that okay for you as well, Lisa? Yeah. Sergeant Deep, make sure you're logged in using your UWS credentials. So that's your banner ID. If you don't do that, you won't be able to log in. So again, all this information is on OneNote. So the group reports, the class tests, Little Man Computer, everything is there. There is a list there of the groups from last year. I've left it up there just to say that once we have the groups set up, I'll put them up here so that you know. Yeah, I know that, Lisa. And part of the reason, so Lisa's saying that she stays quite far away, so do I. So I absolutely understand. It takes me, I've got more than a 2 hour travel for a 2 hour class. So yeah, I feel your pain. So we will talk about what we do for Paisley. But there will be some times where you have to come in. Okay, are you all happy with that? Any other questions just now?
Can I ask a quick question? I just enrolled yesterday and I haven't got my full timetable yet. Do you know how long it will take and where the timetable comes up?
If it hasn't come up today, it'll be there by tomorrow. It's usually overnight. It'll depend when you enroll. So basically all the systems interconnect. And once you enroll, it sort of works its way on. you'll learn about it in here. It's called a batch system. So we run these things overnight or at different times. So it shouldn't be too long for it to come through. If you know the modules that you've chosen, speak to your tutor. So what program are you on?
Year to computer networking.
Tutor networking. I think your class tutor is Duncan, but don't quote me. So speak to Duncan. He'll be able to tell you which classes you have, and you'll be able to get access to them even if they're not yet on your timetable. Having said that, it's Friday, so you'll have them for next week anyway. But if you don't have them by Monday, immediately contact Duncan because you don't want to fall behind.
Yeah, no worries, thanks.
What? Any other questions? Right, I'm acutely aware that I've been talking for a long time. I'm also aware that it's a long time to sit in front of your computer, so I would encourage you to get up, walk around, grab a cup of tea, do anything else that you want to do, and we'll have a second part to this where we'll do the introductory chapter in 10 minutes time. So take a break and I'll see you in 9 minutes and 55 seconds from now.
Okay. Cheers.
Okay, and we're back. Hope you took a wee break, got something to drink. Yep, Alan's supping away there. Excellent. Amazing how long it takes to actually make a cup of tea. Okay, so what we're going to do is do the introductory chapter from our book that you have already bought, I am sure. There was one thing I forgot to say in the first half. I said that our labs, so our on-campus stuff for the first half will be on the Little Man computer. For the second half, it will be dedicated to the group report. So it will allow you to get together in your groups and work in your report, but we'll be there if you have questions or you need help or whatever. So the first half's LMC, second half's the group report. So that said, I want to do the introductory chapter from the book. And one of the things I'll say is, remember I said I've cut down stuff, and I have. So there's our introductory chapter, and you'll see that there are two versions of the slides. And I've cut down quite a lot from this, and there's still 55 slides in it. Now, don't worry. Part of the reason there's 55 slides is it's covering what we're going to do. So what I'm going to do is go through it, give you an idea of what we're going to be doing, but I'm not going to go into any detail on anything, because of course that's what the subsequent chapters are doing. So this bit is just to give you an idea of what's coming up. So I'm not going to go over it in detail. Instead, it's going to be about headings, about what we're going to do, about the fact that we're going to look at how operating systems are put together and all the different bits that we need to make up an operating system, and to figure out what's different in different operating systems. Why is a Mac chosen a different file system to a Windows machine? So we'll look at all that kind of stuff. And of course, we'll start off by asking what actually is an operating system. And the simple answer is it's the bit between the meat and the thing that does something useful. So you want to give a PowerPoint presentation. On my operating system, I have to find the presentation. I have to use my mouse to point to it, and I have to double click it. That then makes an association with the appropriate executable, in this case PowerPoint, and it means that you see that slide up there. I'm the guy at one end pressing a button, PowerPoint's at the other end showing you the presentation, but in between there's a whole lot of other stuff going on. It has to know that I've moved the pointer on the screen, and it has to update that. It has to know when I click the button. If I click the button here, it goes to the next slide. If I click the button on the PowerPoint file, or rather if I double click it, if I click it, it selects it. If I double click it, it runs it. So it has to know the difference between that. It then has to go and get the file, which in my machine is on an SSD. So it goes and gets the file, and it looks at it, and it loads it into working memory, and it figures out what it is, and it realizes it's a PowerPoint file. So it says, oh, actually, I've loaded the file, but I need to load the program that runs it. So it goes away to my SSD and brings back PowerPoint and loads that into working memory. And then it tells the display to update with the PowerPoint interface. And PowerPoint then uses the operating system to display all its buttons and menus and all the other stuff. So the operating system's doing quite a lot. It knows that the thing that I've called Introduction to Operating Systems is located at file location 27856 on my SSD and not file location 1284 on my USB drive, or file location 261593 on my network storage. So it's going to make all those connections as well. So there's an awful lot going on there. It's got to know about the hardware, the screen that I'm watching it on, the CPU that's running the program, the I/O devices like the mouse and the keyboard, the hardware, the hard disk rather, all those other bits and pieces. It has to control all of those. And it has to control them. In my own case, it's just me, but in some operating systems with more than one person using it. But I'm definitely using more than one program. And it has to know which bits get preference, which bits get to use the hard disk first, which program is the mouse talking about. So it has to share out all those resources into all those things that you run on your computer. And it has to spread them not just between those particular applications, but other people, or maybe even other computers. Operating system has to take care of all of that. So you might have multiple users using multiple applications, but they're all controlled by the one operating system that uses the hardware. So the operating system also sits between you and the hardware, both to make sure that you don't mess it up, but also to make sure that everything works together. And you have to decide as part of your decision making about your operating system what you mean by working together and working well. And that might mean different things for different types of system. I've got a Linux box set up with hard disks that I run as a network storage device. I'm not really bothered about it having a nice, fancy graphical interface. In fact, I definitely don't want it to have a graphical interface because I don't want it wasting any resources creating a graphical interface and having a mouse. So instead, I've got a command line interface where I type commands over the network as it happens. So it's got network connections. So it's not as easy to use because I have to type commands, but it's more, it performs better. So those might be two competing demands that we have. It might mean that it works out the resources. And again, part of that is whether the type of interface, but it's also deciding on if I save to my network attached device, which hard disk does it go to? Because I've got multiple ones in there. Does it go to more than one to automatically back up as I'm doing it? And for some systems, and you're all logged into the university systems, it's got to do that for all the people that's on this call. And it's got to assign all those resources between all the people that are on that call and make sure that you're all seeing the video and all hearing me properly and all seeing the slides. So there's a whole bunch of things that it's doing, and there are competing ways that it might want to do them. Whether it's a Windows machine, a Windows workstation, a Windows server, my iPhone, the computer that controls the ABS in my car, because that's got an operating system as well. And all of those things will have different concerns and will concentrate on different things. It will decide which resources things should have. I'm quite glad that the ABS in my car has its own computer and its own operating system, because I don't want the ABS to also be running the same computer that runs the in-car entertainment service. Because I don't want resources taken away from the ABS to be checking what the MP3 is called. You go to press the brake pedal and you get the operating system saying, hang on, I'm just contacting the CD database to find out what the name of this track is. I'll put the brakes on shortly. not really a good idea. So you want resources to be allocated, and you want them to be allocated in the best way possible for what you're doing. I do not want a blue screen of death in my car, because if it happens in my car, it could really be a blue screen of death when I bang into that wall. So it has to set resources, it has to control things and stop you doing stupid things, like overwriting one program with another, or overwriting somebody else's data with something else. So there is no such thing as the operating system. There's only an operating system. This particular operating system, it has this set of functions to do this set of tasks in this particular context. So we'll look at what all those things are. And we'll look at what controls them, which in this case is a kernel. So that's the core program for the operating system itself. The bit that you could say is the operating system. Any of you that have come across Linux, actually a Linux system means a Linux kernel. Most of the other stuff is actually from other places, like the Free Software Foundation or something like that. It's the kernel that's the core of the operating system. And it has to be tailored to the hardware, whether you're running it on a Mac or an iPhone or an Android tablet, it has to be tailored to that hardware. So how does this stuff happen? Well, when you start up, you've probably seen your machine say things like checking what hardware we have. That's called the bootstrap, and that's stored in a wee chip that you'll know about from last year called a ROM, read-only memory, and it runs a small program, and the small program says, okay, I've got a display, and I've got a hard disk, and I've got a keyboard, and I've got a mouse, which actually is my favourite ever error message in the early days of Windows machines. If you didn't have a keyboard attached, it would say, keyboard error, press F1 to continue. And that's a genuine error. So the Bootstrap program runs, checks everything's okay, checks that you've got all your hardware, and then transfers to some other device, typically a hard disk or an SSD or something, and that starts up the operating system. And that operating system runs in the CPU and connects to all the stuff that you have already identified as part of your Bootstrap, all of those hardware devices. Then we have to make sure that they all work. So we have to have connections to all of those I/O devices. And any of you that have ever installed any new device on your machine, you've installed a new mouse or a printer, will know that you install a new program for it. And it's basically a way of saying to the operating system, oh, here's a new printer, here's what you need to tell it to make it print an A on the paper. So all of these devices have their own programs that go with them, that have some space to store data on, to be able to send information from your version of Word to the printer, so that what you create on the screen gets to the paper. All of these things have to be controlled, and clearly we can't do them all at the same time. You should remember from last year that a CPU can only do one thing at a time. And you saw that in the LMC earlier. It's only doing one instruction. One instruction. So what happens if you want something to change? What happens if you're busy typing text into Word and you get a packet in from the network because you're getting a message? Well, you have to stop what you're doing and do something else, and that's called an interrupt. And we'll talk about how they work and how you move from one application to another. Although we won't call them applications because they're processes. Some of these things you don't even know are running, and we'll look at that as well. And we'll look at different ways that we can do interrupts. We'll look at how long they take, what has to happen for these things to be useful, so that our input-output can all work. I mean, we'll look at the kinds of things that we have to set up for that to make that work. We won't be looking at these kinds of definitions because you'll know them from last year. You'll remember bits and kilobytes and megabytes and all that kind of stuff. But we will be looking at different types of storage, how they connect, why we have different types of storage, the trade-offs that we make about how much something costs. So I've got an SSD in my machine that it was much more expensive than the hard disk equivalent, but on the other hand, it's much faster. And those kinds of trade-offs happen everywhere. Of course, everybody wants the fastest CPU and the biggest storage and the largest display screen. But they all cost money. So you make compromises and you decide what's more important. If you do design, you might want a large high-resolution screen because that's important to you. If you play games, you might want a fast CPU. And you certainly want your I/O to be fast so that you don't miss a trigger pull. So we'll look at how these things happen, and we'll look at ways of speeding up devices using things like caching, so that we can have a device going faster even when it's intrinsically slow. So we'll look at how all these things fit together, how they all connect, how information is sent from one to the other, how this caching can speed things up to make it appear that our devices are faster than they actually are. We'll look at other techniques for connecting devices like direct memory access to allow us to transfer information, say, from a hard disk to working storage without having the CPU involved. We'll look at all of these things, including how computers work at the basic level, and that's where the LMC comes in, and it's where what you spoke about in computer systems comes in. All of our modern computers follow something called a von Neumann architecture, which is what you see on screen here. You have a set of instructions, it wanders its way through this set of instructions, executing them until it's told to stop. And again, that's exactly what we did with that wee LMC program earlier. It had a set of instructions that did one after the other, and then we told it to stop. All of the computers that we use do exactly the same thing. They all work in exactly that way that that LMC worked. The computer that you're looking at just now, or the phone that you're looking at just now, or the tablet you're looking at just now, works in exactly that way, albeit more instructions running more quickly. So we all have a processor that executes those instructions. Some of us, if we have more money, have multiple processors where we can have a CPU running one instruction, another CPU running another. We might have them either side by side, so we've got two separate CPUs and we send information to CPUs. They might be bound up into one package, so we've got CPUs with multiple cores, so that we can run multiple things and get more things happening at once. And the sorts of things that we can get happening are increased throughput, economy of scale, increased reliability. And you may be wondering why I'm reading these out. I'm reading these things out because on these slides they are in blue. Blue is your hint. It's your hint that that's the sort of thing that can be asked as a question. Like, name something that a multiprocessor allows you. Would it be A, a different color of computer, B, a bigger screen, C, increased throughput, D, all of the above? When you see blue, remember them. They're important. So we might have multiple processors, each with their registers, each with their own cache. What are registers? That's that thing you saw at the CPU. Local memory storage, like the accumulator. And again, stuff that you should remember from last year. So it might be separate CPUs, it might be one CPU with multiple cores. We might have clustered systems where we have lots of physical computers all working together. And you might see that where you have, say, a movie studio doing some graphics. One dinosaur might be animated by one machine, another by another. A tree might be taken by a third machine, a bush by a fourth. So you send them all out, they get processed, and then they all come back to the center. So you have shared storage, but each computer is connected and runs particular processes on that information. We could have systems where we run processes one after the other, where we don't have any input at all. We were talking earlier about enrolment. So we've got systems at the university that don't require any input, but at say 10 o'clock tonight, we'll look at the enrolled students and we'll create a timetable for them. Why at 10 o'clock at night? Because we're not doing anything else with the computers at 10 o'clock at night. So it makes use of scarce resources. So rather than doing it at 3 o'clock in the afternoon when everybody's on the computer, it does it 10 at night when nobody else is. So we'll use batch systems to run things later on. Or we'll use time-sharing systems, which is what we're doing now on Teams. We've got one central server, and everybody on here gets some time on it to see whether you've typed something in or put your hand up or whatever it is you're happening to do. So we'll look at those different types of system, how we set up the memory for them, how the interrupts work for them, and whether we use hardware or software for speed, how we protect all the information in there, how we stop one program or one user overwriting another program or another user, how we figure out who gets priority, how we stop one person or one process using all of the resources of the computer. You'll all have seen that. You'll all have pressed a button at some time and your computer feels as if it's stopped. It might just be loading a program or something, but you can't do anything else. So how do we cut down on how that feels? In other words, how do we manage all those processes, all those executing processes that we have in our computer? How do we give them enough CPU, enough memory, enough access to all our I/O devices? How do we make them all work together with one CPU executing one instruction? How do we make them all work together to make it feel as if Teams is working at the same time as PowerPoint is working and is running at the same time as OneNote is working? How do we manage that? How do we make it so that all these things synchronize? How do we send information from one to another? How does me clicking on a meeting in Outlook start Teams? How does all that stuff work? How do we communicate? How do we get information from one to the other? How, once we have all those things loaded, do we put them all into memory and not have them all crash together? How do we keep them all separate and make sure process 1 sticks to where it's supposed to be and process 2 sticks to where it's supposed to be and Alan sticks to where he's supposed to be and Liam sticks to where he's supposed to be? How do we keep all these things apart and stop them messing up other people or other people's data? How do we keep all the stuff on our devices, our hard disks, our SSDs, our USBs? How do we know that introduction.ppt is stored at sector 57 on my SSD? What keeps that link? Well, clearly the operating system, or I wouldn't be talking about it, but how does it do it? And there are different ways that we can manage that. And how do we manage that? How do we decide how we do that? How fast will it be to keep it on different devices? Is it better for me to keep my file on a hard disk, on an SSD, on a USB or a network drive? And how do we get it from one place to another? How do we get just like we did with LMC this morning, how do we get an instruction from the hard disk into main memory and running on a CPU hardware register? How do we even connect that hardware in the first place? How do we get those onto our computer and make sure that they all work and that we can have multiple hard disks or USB drives or network storage, and we don't have to care? We don't care whether we're saving a file onto a hard disk or an SSD, we just say save the file. The operating system sorts it out. And it also sorts out whether you can access it or not, whether you can get access to that OneNote, which is stored on a network server on my space on that network server and owned by me, but you're allowed to look at it. Something has to say that you're allowed to look at it, and that's the operating system. But of course, that's on my server, my part of the server, and you're on your machine, so we have to be able to connect computers as well. So how does the operating system cope with all these networks, and how does it know where to send the data and how to do that? And that's without even thinking that you could be on a mobile device, never mind one that's connected to a wire. So what are all those different types of network? And how do we send data from one to the other? Is it going to be smart computers? Is it going to be clients? Is it going to be smartphones? How do we send data? Is something in charge, or do we spread it about amongst lots of places? And if, for example, we want to run multiple things on one device, can we virtualize them? Can we put a Unix operating system on a Windows machine? Well, yes, we can, because we can use virtualization. And if we have an old machine that was installed in 1995, but it runs software and it's important to your company, can we virtualize that machine and run it on a new machine? Well, yes, you can, and IBM make billions of dollars a year doing exactly that. They virtualize environments instead of having physical machines. And sometimes you don't even need to have a box in your office. Sometimes you can just have a connection to a cloud machine that's running somewhere that you don't care about and backed up by somebody that you don't know about. Sometimes you don't even know the operating system exists because it's running in real time on your car or on your Ring doorbell or on a nuclear power station. In either case, you want something to happen in real time. I want my brakes to come on. I want my doorbell to note that somebody's there. I want the nuclear power station to not overheat and go bang. So I kind of want that to happen at exactly the right time. And of course, there's lots of different types of operating systems from different companies, and there's also open source ones that use all sorts of other resources to create them. So we'll be covering all of that. So that was the very quick trot through what we will be doing. 55 slides in 12 minutes. That's quite impressive, I have to say. So you can look at that in detail, but we'll be covering all of that over the next few weeks. Thank you for the applause. That's very kind. Any questions about that?
No, none at all.
Well, as usual, that's on, I've lost my mouse, there it is. That's on chapter 1, and that presentation that we just looked at there is there, and the original presentation from the book is there, so it's got a wee bit more in it. Now, one of the things that I didn't mention when I talked about the chapter tests is we also have chapter tutorials. So every chapter has a chapter tutorial. It's a quiz. Distinguish between client-server and peer-to-peer models of distributed systems. So every week I want you to complete these chapter tutorials and these chapter tests and hand them in, and I will be keeping an eye on whether you've done them. I'm not going to mark them because I want you to be responsible for your learning. So if you're not passing the chapter test, absolutely ask me if there's something that you don't understand, but it's up to you to keep studying till you can pass. Yes, I will help. Absolutely, I will help. That's what I'm here for. But I need you to do your part as well. Similarly with these tutorials, I won't be marking them as such, but if you go through them and you can't find the answer to question 4, then ask, but only after you've tried to do it yourself. Okay, so there are chapter tutorials and chapter reviews and chapter tests for all of the chapters. So your part of what you would do in the lab is that. In following weeks, I certainly won't be speaking for 2 hours, so you can do it as part of this one as well. So we'll cover some of the material and then you can do the tests. Any questions? Okay, I'm not seeing anything, so let me stop the recording.